In this video, we're going to be doing a FRQ for Unit 7 Oscillations of AP Physics 1. A block of mass m rests on a horizontal frictionless table and is attached to a relaxed ideal spring of spring constant k. A second block of mass 2m moves toward the block with an initial speed of v and collides to it and sticks to it, where the collision time is negligible. Derive expressions for the following quantities in terms of m, k, and v only. v1, the speed of the combined blocks immediately after the collision. So actually, because this block is going to be twice the mass, I'll make this 2m, and this is block m of mass m. So this block is going to have an incoming speed of v. We have a spring constant k here, and then they're going to stick. Therefore, we know that it's going to be perfectly inelastic. So after they stick, they're going to have a combined mass that is equal to 2m. Because m plus 2m will be equal to 3m. Or they're going to have a combined mass of 3m, So in order to find v1, we know that because collision time is going to be negligible, that means the external impulse is going to be approximately negligible as well. So that means we can say that we have conservation of linear momentum delta p. So before the collision, we know that m is at rest, so the momentum is going to be 0. And then we know that block 2m is going to move with the speed of v. So that means the momentum will be equal to 2m times v. So here we had m times 0, so that would have been 0. Then after the collision, we had one block that is 3m, the combined mass, and that's going to move with the speed of vf. So then we have 2mv, 3mv. We can see that we have mass on both sides, so that cancels out. So we'll have 2v is equal to 3v1. If we solve for v1, that's equal to 2v over 3. Now, for part 2, we're asked the max compression distance of the spring. Well, we know that in the collision, the 3m is going to move and it's going to compress the spring. So after the collision, instantly, so not much time afterwards, we're going to say that your speed is going to be v1, and then we're going to say that the spring is going to be relaxed. So therefore, we're going to say our spring compression is just equal to 0 after the collision. But then instantly, or when we're at the instant of our max compression, we'll have our speed is equal to 0 because all the kinetic energy will be potential energy. So we have conservation of mechanical energy after the collision. So we know that after the collision, we can write kf is equal to 1/2 3m v1 vf squared. So at the max compression, we'll say our potential energy is equal to 1/2 kx squared. So we have 1/2 3m v1 squared is equal to 1/2 kx squared. We'll cancel 1/2. We'll have 3m v1 squared is equal to kx squared. Now, if we solve for x, we have x squared is equal to 3m v1 vf squared. Change this to vf. So we can take the root of both sides, and x is equal to the root of 3m vf squared over k. If we wanted to, we could take that v out as well. But here, what we're going to do is substitute in the V1 is equal to 2V over 3. So after we do this is VF actually, we'll have X is equal to the root of 3M 2V over 3 squared over K. This will equal to 3M 4V squared over 9 over K. And this will be 12M V squared over 9K. So we know 12 over 9, this is equal to 4 over 3. So we can rewrite this 4mv squared over 3k. So you can also take out this 2, and we can also take this as well out as a v. So we'll have 2v root m over 3k. Now we can continue to part 3. Find t, the period of the subsequent simple harmonic motion of the system. So we know that after collision, we have one mass moving. So we'll call the mass that is going to be oscillating 3m. And then we know that when we have a mass spring oscillator, we'll have, in the horizontal direction, we have 2 pi root m over k. So if we say our m is 3m, right, we'll have t is equal to 2 pi root 3m over k. So that is your period.